Imagine standing on a station platform, listening to the loudspeaker. Train 123. You know the train number, but not which track to wait on. You have to wait for the rest of the announcement, to Delhi, before verifying your destination. A predictive parser experiences this exact same hesitation reading grammar rules. If it sees the word if, but two different productions start with if, a one-token look-ahead is insufficient. The parser hits a wall and stops. In compiler design, we call this a choice conflict, or the common prefix problem. The parser is paralyzed because multiple valid paths begin with the exact same sequence of tokens. To solve this, we use left factoring. It follows basic algebra. If you have the expression AB plus AC, you factor out the common A, rewriting it as A times B plus C. In a grammar, we take rules with a shared prefix, represented by alpha, and factor that prefix out. We isolate the shared parts from the different parts. By grouping the common prefix into a single path, the parser safely consumes the input. We postpone the branching decision until the parser has read enough tokens to know exactly which rule applies. Take two shorthand if-then-else rules. S produces IETS and IETSES. Scanning left to right, we isolate the common prefix, IETS, and write it followed by a new non-terminal, S'. S' holds the differing remainders, ES from the second rule and epsilon for the empty first rule. Epsilon is mathematically necessary. Without it, the parser has no valid path to complete a basic if-then statement, and the parsing process would crash. Epsilon tells the parser it can legally finish the rule without expecting any more characters. This scales to larger blocks, but extraction must be precise. In these overlapping productions, factoring only A leaves paths starting with B. The conflict remains. You must extract the longest common prefix, A, B, mapping true remainders, C, D, and EF, to a new non-terminal. As you prepare grammars, you will encounter two distinct structural problems that break parsers in different ways. Left recursion occurs when a rule calls itself on the extreme left, driving the parser into an infinite loop. Left factoring deals with shared prefixes, which calls a bottleneck where the parser freezes because it has too many valid choices. Left recursion equals a fatal loop. Left factoring equals a choice conflict. A grammar fails with either flaw. You must remove both to function. Take a look at this while loop grammar. We have a standard loop and a loop with an else condition. Find the longest common prefix and mentally factor the rule. The shared sequence is while ES. We factor that out into our base rule, add an S', and then map out our remainders. The second rule leaves us with else S, and the first rule leaves us with nothing, so we cap it with epsilon. Left factoring occupies a specific, immovable spot in compiler design. You take your original grammar, strip out the left recursion, and then execute left factoring. Only after clearing both of those structural hurdles can you move forward to compute your first and follow sets and build an LL1 parsing table. This process successfully removes ambiguity. By isolating the longest common prefix, we reorganize the grammar structure so a predictive parser can read it. Crucially, the actual language generated by these rules remains completely unchanged. A predictive parser operates on limited information. Securing a grammar that is entirely free of left recursion and choice conflicts is the absolute baseline requirement before you write a single line of parser code.